Hello and welcome to part 1 of our multi-part lecture series on the topic of bipolar junction transistors, which is a subsection of electronics. Learning objectives of this lecture include understanding BJT construction, doing a comparison between NPN and PNP BJTs, understanding the mathematical relationships, the equation that relate the base current to the collector current to the emitter current, regions of operation and biasing of BJTs, and DC circuit analysis, particularly the NPN transistors. BJT construction. We've so far looked at a diode, which is in many ways the simplest electronic device. It contains a p-type region which is in contact with the n-type region, and this becomes a junction diode. BJT is formed by doping three semiconductor regions, which are called as emitter, base, and collector, and they are connected. So the emitter is the heavily doped region. So you can see the emitter over here. Base is a thin and lightly doped region. So this is the base, and collector is a moderately doped region. Now you can see that they are junctions. So there is a base emitter junction, and you can see that there is a base collector junction. So in the case of a junction diode, we only had one junction. However, over here you can see more than one junctions. So this is how a BJT is constructed, and now we will take a look at its symbols and different types of BJTs. So we basically have two different types of BJTs. We have an NPN BJT and a PNP BJT. In the case of NPN BJT, the emitter is an N-type region and the base is a P-type region, whereas the collector is also an N-type region. So this is how the junctions will look like. So you have an N junction for the collector, okay, which is this. You have an N junction for the emitter, which is this, and you have a P-type base, okay? So you have one junction here and another junction over here. And this is a symbol of an NPN BJT. I'll explain you the direction of these currents, but for now, you can see that it is shown by this symbol where this side, the plain side, is the base. The side with the arrow is the emitter, and the other side is the collector, okay? In terms of the direction of the current, you can see that the emitter current is pointing away from the arrow, okay? So the collector current is pointing towards the emitter, and the base current is actually entering into the base. So you have to keep this in mind. You don't have to memorize this. This is all given in NCSFE reference handbook. But in terms of just looking at a symbol and identifying whether it's an NPN or a PNP, the simplest thing is that if the arrow is pointing away from the transistor, that's an NPN transistor. Now we have a PNP transistor, PNP BJT. In this case, your emitter is a P-type region. Your base is an N-type region, and your collector is also a P-type region. So this is your collector, this is your base, and this is your emitter. Now in terms of the transistor itself, you can see that the arrow is pointing inwards, okay? It is pointing inwards to the actual transistor. So this arrow indicates that this is where the emitter is, and you can see that the direction of the emitter current is towards this arrow, okay? And in the case of a PNP BJT, the direction of the base current will be away from the base, and the direction of the collector current will be away from the collector. In terms of mathematical relationships, it is very important to understand how the emitter current, the base current, and collector current are connected with each other. So if you look at NPN BJT, it's pretty obvious. If we consider the base as a node, okay, so you can see that basically collector current is entering the node, okay, or just look at the transistor as a node. So the collector current is entering into the transistor, the base current is entering into the transistor, then obviously the emitter current will have to leave because the sum of all the currents is equal to 0, which is indicated here. The emitter current is leaving and the collector current and the base current are entering. So you can say that i.e. the emitter current is equal to the sum of the base current and the collector current. Okay, so that's pretty obvious. And that is true for PNP as well. So you can see over here in this case, the base current and the collector current are leaving, but IE is the one that is entering. So sum of all the currents, that is the sum of the currents that are entering, should be equal to the sum of all the currents that are leaving. The only current that is entering is IE, and the two currents that are leaving are IB plus IC. Okay, so this particular equation is true for both of them. So are the remaining two equations. It's a property of the BJT that the collector current is related to the base current with this relationship. IC is equal to beta times IB, where beta is a transistor DC current gain, and it is a property of the transistor. It would be provided to you in the question, so you don't need to worry about it. And the relationship between IC and IE is this. IC is equal to alpha times IE, where alpha is equal to beta divided by beta plus 1. So alpha is based on beta. So if you know beta, you can figure out both alpha and the relationships between the collector current and the base current, and the collector current and the emitter current. Regions of operation and biasing of BJT. So in the case of diode, we know that it's a very simple device. It's a very important device, but a very simple device, especially the junction diode. It will only allow current in one direction when it's forward biased, and when it's reversed biased, it basically acts as an open circuit. Okay, so it really is a switch on and a switch off circuit, and it only has two states, forward biasing and reverse biasing. In the case of BJT, we have another function, and that is true for all the transistors. We have a mode of operation which is called amplification. Okay, and this is why transistors were such a huge breakthrough in the early 1960s, I believe, or 50s, and they really took off in 60s and 70s because of amplification. Prior to that, amplification would have been done using vacuum tubes, and the CRT TVs, if you're familiar with them, they basically use that type of archaic technology to some extent. But amplification really took on by means of transistors, and that's when the real revolution in electronics started to happen. So the mode of operation really that we are interested in is the active region or the amplification mode, because the diode itself can also act as a closed switch and open switch. Now there are different types of controls. So there are some switches, electronic switches, which are fully controllable. There's some switches which are semi-controllable, and diode is a type of a switch which cannot be controlled essentially. So you can close it or open it based on biasing, but that's a separate topic of discussion which we will touch upon later on in this course. Okay, so for amplification to happen, you have to have the base emitter junction forward biased. Now if you look at both the PNP and NPN, you can basically see that essentially you can look at it as a combination of diodes, right? So there are three regions, agreed, but then there's one PN junction here and another PN junction over here. Same is true for the PNP transistor, because you have one PN junction over here and another PN junction over here. So if you look at each PN junction, you can discuss whether that junction is forward biased or reverse biased. Okay, again, you don't need to remember this. This is all provided in NCSFE reference handbook, but for the BJT to be operating in the active or the amplification mode, the base emitter junction has to be forward biased. Okay, so the base emitter junction has to be forward biased. What it means that is the voltage VBE that is applied across this junction should be greater than 0.7 volts. Okay, so typically 0.7 volts or 0.5 volts is considered the forward biasing voltage. 0.7 volts is more typical, so it will either be provided to you in the question, or you can safely assume that 0.7 volts is the forward bias voltage. And for amplification to happen, the other condition is that the base collector junction should be reverse biased. Okay, so the base collector junction is this. The base collector junction is this. So VBC should be less than 0.7 volts. So VBE should be greater than 0.7 volts, whereas VBC should be less than 0.7 volts. The next region is saturation region, which is essentially a switch on. So when it's operating in the saturation region, the BJT acts as a short wire, for lack of a better term, right? So this is what we observed in the case of diode. When it is forward biased, it really doesn't offer any resistance. And if it's a non-ideal diode, there would be a 0.7 volt voltage drop. So for the BJT to operate in the saturation region, the base emitter junction is forward biased. So it basically means that a base emitter junction, VBE, is going to be greater than 0.7 volts, but the base collector junction is also forward biased. Okay, so the VBC is also greater than 0.7 volts. So when these two conditions are met, the BJT would be biased in the saturation region. There won't be any amplification happening, but the BJT will act as a closed switch. So it will basically act as a short. And finally, we have the cutoff region in which BJT will act like an open switch or a switch off. And for this to happen, the base emitter junction is reverse biased. So this is the base emitter junction. VBE has to be less than 0.7 volts. And the base collector junction, which is this, VBC, it has to be less than 0.7 volts as well. So these are the three regions of operation and biasing of the BJTs. Now we can potentially discuss what exactly happens in the amplification mode, what exactly happens in the saturation mode. We can discuss in the context of energy bands and so on. But in my opinion, that is outside the scope for the FE exam. It is more relevant if you're taking a full-blown course on electronics, right? And even from a question standpoint, I would personally be paying more attention and more focus on circuit analysis and biasing of BJT circuits. But this much theory is important to understand. Okay, it is important to realize that depending on how you're setting the voltages across these junctions, your transistor may or may not be in one of these modes. Okay, and really the biasing would determine whether your transistor is going to do amplification, or whether the transistor is going to act as a switch on or as a switch off. The next logical step in our discussion is DC circuit analysis. So we just touched upon biasing. Now we are going to look at how we can evaluate the state of the BJT circuit. So remember in the last lecture, lecture series I should call it, when we were looking at the circuit analysis of diodes, we actually always started, especially when you have multiple diodes, by assuming an operating mode. Okay, so if you want to quickly go back to those lectures, please feel free to jump back, because if you remember that example where we had two different diodes, D1 and D2, so we started by assuming that we thought that, okay, let's assume that both diodes are on, and then we checked our assumptions, and then we had to turn one of the diodes off. Essentially, it's the same process over here, but you're working with one transistor circuit. But within that transistor circuit, the transistor itself can be in three different modes of operation. So step number one is always to assume an operating mode, that is active, saturation, or cutoff. And remember that amplification for the BJT happens in the active region. So it's typically recommended to begin by active region unless you can observe right away that the BJT is biased such that both junctions VBE and VBC are actually reverse biased, so you can determine cutoff. Saturation is not that easy to just eyeball, because you really have to determine those voltages, right? So my advice is always to assume amplification mode unless you can tell right away, depending on biasing, that it is a cutoff. Then you enforce conditions which are relevant for the region of operation. So if you're assuming that it's amplification mode, then you know that all the currents IB, IE, and IC will be greater than 0. Okay, and VBE in the case of amplification is equal to 0.7 volts. So you have to analyze the circuit and calculate the unknown currents and voltages. So you have to then go ahead, calculate IB, IC, IE, as well as VCE and VBC, and that will basically help you determine whether actually the BJT is in the active region amplification mode or not. And finally, just compare the results with the assumption. If they are consistent, then you're done. Otherwise, you will have to go back to step number 1 and assume a different state of operation. So typically you would assume that it's in cutoff region, especially if one of these currents are turning out to be negative or 0, then cutoff is the next logical assumption to make. Now we will go through a bunch of these circuits, because just explaining these steps, in my opinion, are not sufficient. But when you see how they are implemented in action by means of examples, hopefully it will help address any questions that you may have at this point, and also provide you additional practice. So this is our example number 1. We are provided a BJT circuit, and we are being asked to calculate the collector current if beta is equal to 75. Okay, remember beta is the DC current gain of this BJT. So a couple of things that I'd like to point out is that, first of all, this is an NPN BJT. Now in this lecture, we are just going to look at DC circuit analysis of NPN BJTs. In the next lecture, we will look at PNP as well, because I wanted to keep it relatively simple, especially for this introductory lecture. At the same time, give you some examples of DC circuit analysis. So this is a NPN BJT, and the beta is provided to you. Another thing that you can notice is that your emitter current has a current source, which basically means that the emitter current is fixed. Okay, so your IE is fixed to 1 milliamp. This is an important observation to make. The other important piece of information that's provided to you is VC. So your collector voltage is 2 volts. Based on the mathematical relationships that we explored earlier, we know that the emitter current is equal to the base current plus the collector current, and the equation that relates the collector current to the base current is this, and the equation that relates the collector current to the emitter current is this. Now we have already been provided IE, which is equal to 1 milliamp. I just explained to you that this is a very important observation that you have to make. Otherwise, you won't be able to really make much headway with this particular problem. Okay, so your IE is fixed to 1 milliamp and beta is equal to 75. So we know IE and we know beta, and we know that alpha is actually related, can be expressed in the form of beta. So we can easily figure out IC. Okay, remember I told you that alpha is equal to beta divided by beta plus 1. So you basically substitute the value of beta in here, you substitute the value of IE in here, and that will give you your IC. And IC is equal to 0.98 milliamp. Another tip that I would like to give you is that if the value of beta is fairly high, and fairly high, I would say that if it's higher than 50, okay, then IE will always be almost equal to IC. Okay, so the reason is that IC is equal to alpha times IE. Now alpha is equal to beta divided by beta plus 1. Okay, so if you're looking at a small value of beta, which typically is not the case, the value of betas would be higher than 50 in most of the cases, right? Let's say the value of beta is very low. Let's say the value of beta is 1. Then you're looking at 1 divided by 1 plus 1, which is 0.5. In that case, your IC will be 50% of your IE. But if your beta is 50 or higher, then you're dividing 50 divided by 51, which is really greater than 90%, right? So 50 divided by 51 would be, I believe, 90, 98, 99%. Okay, so you can see that it would be pretty close. So in this case, we had 75. So 75 was basically 98%, right? If it's 100, then 100 divided by 101 will be almost 99%. The next problem is asking us to determine the region of operation of this NPN BJT. As I mentioned, our first step is always to assume a region of operation, and typically you start out by assuming that the BJT is operating in the active region. Okay, in this case, I can clearly see since IE is greater than 0, it's obvious that this is not cutoff region, right? And the BJT is not operating in the cutoff mode, because in cutoff mode you would have current, you won't have positive currents. If IE is positive, then it means that IC is positive, and that would mean that the IB is positive. Okay, so you're either in the active region or the saturation region. So typically between active and saturation region, the recommendation is always to assume active region. Now in active region, we know that the base emitter junction is forward biased. Okay, so the voltage drop would be 0.7 volts across VBE. And we already know that IC is equal to beta times IB. Okay, so we will calculate the base current, and the base current is equal to 0.98 milliamps. This is IC that we calculated in the previous problem. Okay, 0.98 milliamps divided by 75, that gives us 13.1 microamps. Now IB, we can see that this voltage over here is VB, and this voltage over here is 0 volts because it's grounded. And for the NPN transistor, the direction of the base current is this. Okay, so you can see that 0 volt in this case has to be a higher voltage than VB. Okay, so IB is equal to 0 minus VB divided by 50 kilo ohm. When you solve this, you find that the value of VB is equal to minus 0.65 volts. We also know that VBE is equal to 0.7 volts, which basically means that VB minus VE is equal to 0.7 volts. And you rearrange this equation, and then you basically find that VE is equal to minus 1.35 volts. So in these steps, we are basically finding the unknown currents and unknown voltages, right? We already knew IE and IC, so we went ahead and found IB. Once we found IB, it helped us find VB, and finding VB helped us find VE. So you want to be able to find all of these critical voltages and currents. Okay, so VC is already provided in the problem, which is equal to 2 volts. The other junction that we are interested in is VCE. So VCE is equal to VC minus VE. Okay, so VC we just established, it's provided, it's 2 volts, and VE we know it's minus 1.35 volts. And when you solve that, you basically find that VC is equal to 3.35 volts, which is greater than 0.7 volts. So in some textbooks, you will basically find this condition that they ask you to check whether it is operating in the active region or not. Okay, if VCE is greater than 0.7 volts, you're good. In NCSFE reference handbook, you have VBC. Okay, the VBC needs to be checked, and VBC has to be less than 0.7 volts. So you'll find that VBC is equal to VB minus VC. We know VB, we know VC, and we find that it's minus 4 volts, which is less than 0.7 volts. So VBC is actually reverse biased, which meets the requirement for active region, because for active region, you have to have VBE forward biased. The other condition is that IB should be greater than 0, IC should be greater than 0, and IE should be greater than 0. I didn't mention it there, but in active region and saturation region, in active mode and saturation mode, you have all of these currents positive, whereas in the cutoff mode, all of these currents are equal to 0. So that's one requirement. This is cutoff. Okay, and just by looking at the currents, you can tell, right? This could potentially be active, and this could be saturation as well. Okay, but now that you've confirmed that your VCE is greater than 0.7 and your VBC is less than 0.7, okay, now you can confirm that your mode of operation is actually active region. Let us now take a look at another practice problem. This is a relatively simple practice problem, especially the fact that we have already analyzed most of the circuit. We are being asked to find the value of the collector resistance RC. If you noticed when we were solving example number 1 and example number 2, we really didn't have to worry about RC because VC was already provided to us. That may not always be the case, right? But in this case, the question didn't explicitly mention what RC is. So that is the only unknown that's left in the circuit. So let's analyze this. We know that the flow of the collector current is this, okay? So the current always flows from a higher potential to a lower potential. So the potential across IC is 5 volts, which is the higher potential, minus VC, which is the lower potential, divided by RC. And your RC would simply be equal to 5 volts minus 2 volts divided by 0.98 milliamps, which is almost equal to 3 kilo ohms. So with this piece of information, we have now completely analyzed this transistor circuit. So we've completed the DC analysis. We know all the voltages, we know all the currents. We also know the mode of operation of this NPN BJT. So this circuit has been completely analyzed. So these are the steps that are involved in analysis of relatively simple BJT circuits. And in the next problem, we are going to analyze a much more complicated NPN BJT circuit. So the basics will remain the same. I have this problem from study guide for FE Electrical and Computer CBT exam. And in this problem, we are being asked to find the value of current IC and the voltage VCE for the BJT. Okay, so typically by the time you determine IC and VCE, you basically analyze the entire BJT. Okay, they are also known as the Q point. And these Q points, once you establish them, you also know the mode of operation of the BJT, okay, or the MOSFET. Because in order to establish what the VCE is and what IC is, you have to first of all determine the state of operation. And we will go through all of the 4 or 5 steps that I mentioned earlier in the lecture systematically in order to analyze this circuit. So these steps are going to be very similar to what we've already seen in the previous examples, but as I mentioned, this is slightly more complicated and advanced level BJT circuit, but definitely a fair game for FE style problems because it involves a few steps and it requires you to bring your DC analysis knowledge to use. So I am not handing out any freebies over here. So remember in the previous one, I told you explicitly what IE was because there was a current source connected. I told you exactly what the VC was, right? It had been pointed out as 2 volts. So if you now go back to those and the circuit, you'll see that in the absence of these 2 details, that circuit would have been complicated, right? So that was an introductory type of circuit. And in this case, we will have to figure out all of these unknowns by actually doing the complete DC analysis. So step number 1 is always to assume a state of operation and we enforce the conditions and then verify the assumptions, okay? So let us assume that the transistor is operating in the active region. In the active region, we have VBE is equal to 0.7 volts, as I mentioned. So this is forward biased, VBE, and IB will be greater than 0. So the current is positive. Similarly, if IB is greater than 0, then you know that IC is related to IB by beta, and IC and IE are related by alpha. So in this case, we will use these assumptions because we have assumed that we are operating in the active region. And VCE, so this is a check, okay? So this is really a check. We have to, at the end, after analyzing this circuit, we have to check our assumptions. And this is the check that we are going to review against. VCE has to be greater than 0.7 volts. So we will write 2 KVL equations. Okay, the first KVL equation, and this is pretty typical for NPN circuit analysis. You will write 1 KVL equation from the base to emitter. This is how that KVL equation is going to look like. And the other KVL equation is going to be from the collector to the emitter. So for the base emitter KVL, we can basically see that we have a 3 volt voltage source, so there is a voltage gain. And then we have VBE over here, which is equal to 0.7 volts. So this will be like this, right? So positive, negative. So that will essentially be a voltage drop. So minus VBE. And then there will be a voltage drop across the 2 kilo ohm resistor. But note that the voltage drop across the 2 kilo ohm resistor will be caused by IE, by the emitter current, okay? Once you enter this region, it's basically emitter current. And the sum of all of that is equal to 0. Now you can rearrange that equation to figure out what the value of IE is going to be. IE will be equal to 1.15 milliamps. Now once you know your IE, you can actually calculate your base current. So your base current will be 1.13 by 10 raised to the power minus 5 amps. And once you find your IB, you can find your IC. You can find your IC from IE as well. It's not a big deal. And you can notice that IE and IC, as I explained you previously, are very close, 1.13 milliamps and 1.15 milliamps. That's because your beta is very high. So now if we do a quick review, and you can pause this lecture at any time if you want to look at these steps in more detail. But essentially what we've figured out by now is our IE, our IB, and our IC. So with this information, we are going to proceed to the next KVL equation, and then we will start finding the voltages. So actually we can write a KCL. We can write a KCL at the collector. So you can find that your IC, which we basically calculated in the last step, is equal to 7 volts minus the collector voltage divided by 3 kilo ohm. Okay, so 7 minus VC divided by 3 kilo ohm, which basically means that our VC will be equal to 3.58 volts. And our VBE is equal to VB minus VE. Okay, we know that based on our assumption, the base emitter has to be forward biased. So VBE is set to 0.7 volts, which basically means that VB is equal to VB minus VE, which is 0.7 volts. And then we solve it for VE and we find that VE is equal to 2.3 volts. So we just found VC over here and we found VE over here. So VCE will now be equal to VC minus VE, which is equal to 3.6 minus 2.3 volts, which is 1.3 volts. Now VCE is greater than 0.7 volts. It basically means that one of the checks is made. And then you have IB, which is greater than 0 milliamps. Your IE is greater than 0 milliamps. And your IC is greater than 0 milliamps. So all the currents are positive, so the second check is also made. Now you can confirm that VBC will be negative, okay, will be negative, less than 0, all right, 0.7 actually, it should be reverse biased. But as I mentioned before, in some textbooks you will see this condition. In NCSFE reference handbook you'll see this condition, but you can verify it yourself that that will be the case. So that basically confirms that the transistor is operating in the active mode. And now the final answer would basically be in the form of your IC and VCE. So VCE we calculated is 1.3 volts and your IC is 1.138 milliamps. So the final answer is D, 1.13 milliamps and 1.3 volts. So in this lecture, we introduced BJTs. We looked at the construction of BJT. We did a comparison between NP and NPNP BJTs. We looked at the mathematical equations that relate the emitter current, the base current, and the collector current. We looked at regions of operation of BJT, the biasing, and we did 3 or 4 different examples of circuit analysis, different steps that are involved in circuit analysis. These steps are very important to remember. Okay, they are not clearly laid out in NCSFE reference handbook. Over there they provide you the conditions, but you have to have this methodology, okay, and this will come with practice. So assume an operating region, enforce the conditions, perform the circuit analysis, essentially find out the unknown currents and voltages, and then finally check the assumptions. I guess that if you're good with circuit analysis, this is probably the only step that is relevant, and it's a very important step, okay, it's a very important step. But the difference between just doing a circuit analysis and actually applying your knowledge of electronics and transistors is basically contained in steps 1 and 2 and step number 4. Okay, so being able to check the assumption, what the forward biasing and the reverse biasing means, what are the different regions of operation, what are the conditions that you need to enforce, that essentially is outside the scope of circuit analysis. So the circuit analysis techniques that we have learned so far will help you perform step number 3 only, but your understanding of electronics will actually help you go through the remaining steps. For further practice, I would recommend you to check out the quiz at the end of the lecture and also consider the problem set in the study guide and the practice exams. I've also prepared a mini exam for you at the end of the section, so be sure to check that out as well to get additional practice. In the next lecture, we will look at PNP and some of the other concepts related to BJT. Thank you. If you found this preview lecture helpful, I'm confident that you will also greatly benefit from the full course that contains over 150 plus lectures and covers all the topics that are found in the latest NCS FE Electrical and Computer Exam specification. You will also find numerous quizzes and mini exams in this course, which will help you in getting additional practice. I have included a link in the description of this YouTube video for a free FE Electrical and Computer Exam preparation webinar. All you need to do is to click the link and sign up. One last thing. Here's a small trailer of Study for FE's on-demand FE Electrical and Computer Exam preparation course. Thanks for watching.